Welcome back. In this lecture, we are going to summarize mass energy balance for open system. So, we will start with the conservation of mass principle. For a simple control volume as depicted here, the total or the conservation of mass principle says that the net mass transfer to and from a control volume during an interval time delta t is equal to the net change in the total mass within the control volume during delta t or the time interval. So, in a simpler form, one can simply write down in expression the total mass entering the control volume during a certain time interval minus total mass leaving the control volume during delta t, and that should be same as that should be equal to net change in mass within the control volume delta t, or in the word m in minus m out is equal to delta m control volume. For in the case of rate expression, you will be considering dots here, and this will be your dm by dt. For a steady flow process, the mass of the control volume will remain constant, and hence this expression, this will be 0, okay. This will turn out to be 0 for steady flow process, and thus you will have m in minus is equal to m out. For many inlets and outlets, this will be a generic expression for the case of steady flow process. Now, in many systems, of course, there are many inlets and outlets. So, one for a simple steady flow process, an example would be, let us say, if you have two inlets, you have M1 and M2, and if there is outlet is 1, then based on simple your M in is equal to M out, okay. Your M in is M1 plus M2, and that should be same as M3, okay. But in many engineering devices such as nozzles, diffusers, turbine, compressors and pumps, they involve only a single stream. In such case, you have M1 is equal to M2, or the M1 dot is equal to M2, okay, and this you can represent in terms of density, volumetric flow rate and cross sectional area as well. Okay, so since we are talking about energy balance also, so and we know that for generic expression the net energy balance would be through heat, work as well as from mass, okay. So, let me just talk about component which we have not discussed earlier. Now, for a flow system and for a steady state system, for a steady flow system, the fluid continuously flows through the inlet and exit through the outlet. And in order to maintain the control volume in the steady state, there will be work which is needed to continuously flow. Now, there will be work which we need to push the certain mass here before the inlet, okay, and similarly there will be work which will have to be pushed out, okay, in order to maintain the continuity. So, let us consider again. So, this is the pressure or volume of the element of the flow which need to be pushed in, and this work which we say is work of flow work or flow energy, okay. So, this is before the entering and this is after the entering, okay. And so, consider this that this pushing this work is being done by some imaginary piston, okay. There is a certain force which is being applied, and this is basically the steady state. There is no acceleration, and the constant force is being applied, and this mass gets in. So, the question is, what is basically the work for such a case, okay. So, let me just take a simpler view of it. So, this is again the force, and this element here, okay, have to be pushed in by a certain distance L, and this force in absence of acceleration is equal to the force applied on the piston. So, this will be equal to the opposite force here, assuming this to be a slow process, is P into A is going to be the force, okay. Now, this work would be the force multiplied by the distance L, and that will be P A L, that will be P into volume, okay. Now, in terms of kilojoules, this will be P into specific volume. So, this will be the work of flow. Of course, the PV value here and PV value in the outlet may be different, okay, because that will depend also on the pressure of the outlet, okay, and the specific volume of the outlet. So, that means there is some PV work here which is associated with it, and there is also PV work associated with the outlet. Now, we can summarize this concept in terms of comparing both the case of non-flowing and the flowing fluid. For the non-flowing fluid, you have energy of the fluid has internal energy energy of the fluid contains internal energy, kinetic energy, potential energy as shown here. So, this internal energy per unit mass, the kinetic energy and the potential energy. For the case of a flowing fluid, in addition to that internal energy, kinetic energy and the potential energy, it also poses a flow energy, because it moves inside and certainly outside. So, it contains that energy, and we use that energy as a part of the energy of the flowing fluid, as PV. Okay. Or in other words, we can also make use of the basic definition, this U plus PV comes in the flowing case, and this can be written as simply H. Okay. So, again we go back to the generic the energy balance, that is E in minus E out is equal to E dE system by dt, and we are considering the rate expression. Okay, considering is a flow process. Now, in this case the net energy transfer is heat, work and due to heat, work and mass. Okay, for the case of a steady state, of course E in is equal to E out. So, if we know the directions of various different interactions, we can write this expression where Q in plus Q out, okay, this is part of E in plus whatever the contribution due to the flow, that is mass, that will be your enthalpy plus kinetic energy plus G Z, okay, potential energy, and that should be equal to Q out W out plus the energy contained by the flowing mass. So, that will be M H. Okay. Now, this is summation is for each inlet and summation here is for each outlet. Okay. So, this is for the case where we know the directions here. We can write also in terms of very generic expression, that would be Q net in, okay, this will be Q net in and Q net W net out, this equal to the summation for the case of outlet, that means it is summation of m dot theta minus summation of m dot theta, this is for in and this will be out. Okay. The change in the energy due to the mass flowing mass. Okay. For a single stream, of course, you are going to consider only H2 minus H1. Most of the time we will be ignoring this velocity and kinetic energy and potential energy, and only for some cases we have to use that. Okay. So, for the case of where we ignore this two terms, we will have Q minus W in terms of per unit mass Q, where if you divide this Q here is going to be small q is Q dot divided by m dot, and thus you can write a very simpler case here, which is Q minus W is equal to H2 minus H1. Okay. So, very simple expressions for energy balances. You can apply these for many devices. I am not going to go through in detail for all the devices, and I expect that some of the exercises you have done that in earlier, but we will just recap how to do this for a few cases. So, for example, nozzle and diffusers are typically used to change the fluid velocity and kinetic energy, whereas there is no heat interaction and the work, the boundary does not change. So, that is your Q and W's are zeros, delta P are going to be also considered to be 0. So, you can apply this basic definition and you get E in is equal to E out, or in the word M H1 plus V1 by V2, V1 square by 2 is equal to M H2 plus V2 square by 2. Now, you can do this analysis knowing the inlet and outlet conditions and the ones unknown variables. You can find out by using simple algebra. Okay, so this is the final expression of that, and you can do the analysis subsequently. Now, the similar kind of exercises you can do for turbine, which is a work producing device, for compressor, fans and pumps, again where the work is needed in order to change the pressures. So, you can do these exercises again based on very simple logics. Okay. For example, this is the case for compressor, where air is being compressed from 100 kilopascal to 600 kilopascal, whereas the flow rate of mass is given here 0.02 kg per second, and what we need to find out is the work which is required, the rate of work which is required, and in this process the heat is also lost. So, you can start with again the basic definition of energy balance here, whereas this is a steady state, then you can consider this and then you can write this E in minus is equal to E out. Now, knowing the direction here already, we can simply write W in plus the flow contribution mH1, this is going to be equal to Q out plus mH2. Okay. So, Q out is here, this part plus mH2 is due to this. Okay. So, you can rewrite this expression in this form. Now, this you can find it from the tables, or you can use Cp dt this if you know the expression in terms of Cp in terms of temperature, and Q out also of course we know that. Now, this kind of analysis is of course applicable to other cases, throttling valve, mixing, heat exchanger and so forth. So, I am not again going to in details of that. You can apply and then revisit some of the example to hone your skills again. Now, I will just talk about the case where we have unsteady flow process, which is also very common. These are the processes where there are changes in the within the control volume with time. Such processes are called a transient flow process, or as I said, unsteady flow. Okay. The examples are discharge of the fluid from pressurized vessel, inflating tires of the balloon. Okay. So, for example, here in this case during this process of the filling of the control volume, this piston can also move. Okay. So, let me just quickly explain how to work with this kind of system. So, most steady flow processes can be represented by uniform flow process, where we assume that the fluid flow at any inlet or exit is uniform and steady, and thus the fluid properties do not change with time or position over the cross section of an inlet or exit, and if they do, they are averaged and treated as constant for the entire process. So, for such a case we can simply write mass balance as m in minus m out is equal to delta m system, where delta m system is m final minus m initial. Sometimes also we write m I inlet and exit is equal to m2 minus m1 of the control volume. Okay. So, this is our mass balance. What about the energy balance? So, we will write again here energy balance E in minus E out is equal to delta E system. Now, delta E system is not going to be 0. In this case, delta E system is m2 E2 minus m1 E1, where this contains only the internal energy, potential energy, kinetic energy as shown here. Okay. Whereas, E in is Q in plus Q W in plus summation of m theta, where theta contains H because it is a flowing fluid, and Ke plus Pe, whereas for the case of outlet is Q out plus W out plus summation m theta for the outlet. Okay. Now, assuming Pe and Ke changes are negligible, you can write down the generic expression in this form. Okay. Q, where Q is net heat minus W is net work out, and this equal to summation mH minus summation, this equal to the contribution due to the changes in the enthalpy from the outlet and inlet, and as well as the changes due to the internal energy of the system. Now, the question is how do you apply this? So, we will take up one example, and this we will end the lecture with this example. This is an example where you have an insulated 8 meter cube rigid tank which contains air at 600 kilopascal, 400 at 400 Kelvin, and the valve is connected to the tank, which is now opened. Air is allowed to escape until the pressure inside the drops to 200 kilopascal. Okay. The air temperature during the process is maintained constant. So, this is maintained. Okay. And by how it is maintained? By providing this electrical resistance. So, there is a electrical work is applied to the system, and what we need to find is basically the electrical energy supplied to the air during this process. Okay. During the process where the pressure is changed from 600 to 200 Kelvin, keeping the temperature constant. Okay. So, the first thing is, since the valve is opened, certain mass has escaped. So, we will be applying the mass balance first, followed by energy balance. So, m in or m in minus m exit is equal to m2 minus m1 of control volume. Now, there is no inlet. So, this m exit is nothing but m1 minus m2, okay, of control volume. Now, E in minus E out is delta E system. Okay. What is E in? W E in here, and what is E out? Because only the mass flow, then we can simply write m E H E, ignoring the kinetic energy and potential energy. So, and as well as since it is insulated. So, Q delta E, delta Ke and delta Pe are going to be 0, okay. And this is M2 U2 minus M1 U1, okay. Now, V1 is constant, okay, P1 we know, P2 we know. Now, the thing is it is air, okay. So, we can consider air to be ideal gas, and thus we can make use of the equation, ideal gas equation, to obtain M1, which will be your molar mass P1 V1 by RT1, and this itself is 0.287 kilopascal meter cube per kg Kelvin. And if you plug in the P1 and V1, P1 is 600 kilopascal, T1 is and T1 and T2 is constant, V1 and V2 is also constant, is V 41.81 kg. Okay. Similarly, you can get M2, M P2 V2 by T2, you get 13.94 kg. Okay. Thus, you can obtain Me, which is M1 minus M2, 27.87 kg. Okay. So, now knowing this Me, okay, we can now plug in this equation. Okay. So, you can plug in this information Me, and what about He? So, you can plug in 2 will become W in, and you can rearrange here, this is Me He plus M2 U2 minus M1 U1. Okay. The reason we have taken again this is because this is the delta E of the system, which is non-flowing, is only of the control volume, and this U, since its ideal gas is only depends on the temperature, which is 400 Kelvin. You can use the table given in any book, okay, and this comes out to be 286.16 kilojoules. Similarly, He, which He is basically the enthalpy, okay, which can be approximated because this can be enthalpy of the air at 400 Kelvin, okay, because enthalpy is the temperatures are fixed for the air, and this from the table also we can get there. So, with this information and with the value Me which we have calculated, we know M2 M1 as well. This value W in comes out to be 3200 kilojoules. Okay. Okay. So, with this we will complete this lecture, and we have just covered the energy balance for the open system. So, we will continue our reviewing process of basic engineering thermodynamics first. So, with that I will end this lecture, and I will see you in the next lecture.